All right, so today we will deal with something's going on with my mouse here. We're going to deal with sampling distributions. So that's chapter 5. And then we will also deal with confidence intervals. Which is our first entry in statistical inference. And that's chapter 6. So I want to, maybe I can pull up that lecture slide from long ago. First day of class. Where is it? Here, okay. So I said, we started off with data collection and data description. We talked about statistics as ways, as numeric summaries to kind of compress data into just a single number. We dealt a little bit with probability itself and probability distributions, such as the normal distribution and the binomial distribution. That will come into play today as we learn about sampling distributions, which will be the first half of the class. And then we will bring that into statistical inference, which is, I would argue, the bulk, or going to be the remaining portion of our course here, okay? And I'll get into all the types of statistical inference that we might encounter. And today we will do our very first step. Do you guys remember from the first week what I said the point, why we even bother studying statistics is? Let's see if that's in one of my slides here. It should be. Okay. Statistics allows us to make conclusions from limited data. That's what I was kind of trying to argue, being that there is a thing that we want to understand about the population, and the population being too big for us to study directly. So instead we deal with a sample, and based on the sample, which is a small data set that we can observe, we're going to make conclusions about the population. And we'll do our first example of that today with confidence intervals. So it's exciting. All right. Let's see. Today, Stats 13, April 23, slide 1. Okay, so let's talk about sampling distributions. So imagine there is a giant entity called the population, which is far too large for us to observe directly. Remember, the population includes everybody that is possibly related to the research question that you have in mind. Okay, so let's say your research question is, do mice develop liver tumors at a greater rate if they're exposed to E. coli, or whatever it might be, okay? The population would be everything that's relevant to that research question, and in that case, or every possible subject, so that would be all mice that could possibly be exposed to E. coli or whatnot. All mice would be considered your population. Of course, that is far too many specimens or things to observe directly, so we're forced to observe a sample. Okay, so from the population, you can imagine just this tiny little thing from the population, which is our sample, and we observe the sample instead, right? So population would be all mice, or whatever it might be. All mice, also too big to observe directly. And from that population, we draw a sample. So actually, do they have increased liver tumors? It's not a good example for this case. Maybe we just want to know what's the average weight of a mouse, maybe for a certain species of mouse. Okay, so I don't know how many mice species there are, but let's say there's just, you pick a species and we just want to know what is the average weight of a mouse. Okay, so the only way to get the true value for that is we would have to look at all the mice ever in the population, and then we would weigh them all and divide by how many we have, and we get the average value. That sounds like way too much work. Okay, so let's just assume we can take a random sample, and that's a tricky question or task to do in of itself, but let's say we were able to obtain a random sample. Okay, so we obtain a random sample. Okay, and from that random sample, we measure the mean weight. Okay, so maybe I'll put this down here. So from the random sample, we record y bar. Okay, we record the mean weight of mice in our random sample. Okay. Let's see. What is... Oh no, I don't want Firefox updated right now. Maybe later. Oh, something happened. Okay. All right. What is the average weight of mouse? Yeah. All right. So, according to House Mouse, typically 10 to 25 grams. That's quite a large spread here. Okay. So let's say we take a sample and our y bar ends up being 16.3 grams. Okay. And we have no idea. Okay, we don't really know a whole lot about mice, but there we have it. Okay. We want to get an idea of all mice ever. Okay. What is the true average weight of all mice? Okay. Well, from looking at one sample directly, it's hard to say anything about the population. Okay, we're gonna try to do that later on in chapter 6. But we could imagine, okay, let's say we had just some magical ability to just obtain a bunch of random samples. Okay, we can create something called a sampling distribution. Let's say we by taking another sample and we record y bar, and then we take another sample and we record y bar. Okay, and we just do this over and over and over again. If this is our population, and I were to just repeatedly take many samples, okay, so do this many times, okay, I would generate a whole bunch of different y bars, right? I would generate a whole bunch of different sample means. And the question is, what would all of those y bars look like? What would the distribution of y bars look like? Okay. Well, the distribution of y bars is known as the sampling distribution of y bar. but that's what we're going for. Okay. So the distribution of the different sample means the y bars is called the sampling distribution of y bar. Okay. So I'll let you guys write that, and I'm just going to say it one more time just so we understand what we're doing, and then I'm going to demonstrate the generation of a sampling distribution. Okay. So, for example, let's do a sampling distribution for the y bar of women's heights. Okay. So our population would be all women. Okay. Let's do all women in the U.S. just because I'm more familiar with heights of women in the United States. Oops. And not the world. Okay, so population is all women in the U.S. and let's say that in the United States the mean height is 64.5 inches with a standard deviation of 3 inches. Okay, so this defines our population. Let's say I take a random sample of 10 women, 10 randomly selected women, and I measure the mean of these 10 randomly selected women. What do you think the mean height would be of 10 randomly selected women? Well, it could be anything, all right? Is it going to necessarily be 64.5? No, let's just say, for example, we got 64.1. Okay, that could very well happen, right? Let's take another sample of another 10 women. And let's say in this case I got 65.3 as the mean height of these 10 randomly selected women. Okay? And we're going to repeat this over and over and over again. Each time we get y bar, each time we select 10 people, but our y bar is probably going to be something a little bit different. Okay, so we just repeat this many times. Okay, is that all right? What do you think the distribution of y bars will look like? Okay, what does our population distribution look like? I'm just going to say it's, you know, normal, mean 64.5, standard deviation equal to 3, so we have a shape like that. What will the distribution of y bars look like? That's what we want to know. What will the sampling distribution of y bar look like? That's what we want to know. Okay. Is this hypothetical question okay? All right, so I'm going to try our hand with oh, look at this guy, so cute. Until he's in your house. Let's use our studio. Do some work here. Forgot me already. Why am I having trouble? This one. Something's going on here. Okay, I might have to do use RStudio on my own computer here, but it's okay. So my I have my RStudio set up a little differently, but that's okay. Okay, so what I'm going to do is I'm going to create a population, okay? So I'm going to simulate a population, and I'm going to just have RStudio generate, we'll say 100,000 people, so that's 10 to the 5th, and we will create the mean of 4, 64.5, and a standard deviation of 3, okay? And I'm just going to have it round off to 0, okay? So everybody self-reports when they report their height, they just round off to the nearest inch. So I say, how tall are you? You're going to say I'm 5'3", or you're going to say I'm 5'4". No one's going to answer 5'3.2", okay? All right, and so we can say, well, give me the histogram of what this thing looks like. So the histogram of our population, and we'll ask for a little bit more detail. We'll say breaks is equal to 30, and this is what our histogram looks like. Okay, so for the mean, so we see, okay, so most women are around 64 inches tall. Oh, I'm so sorry, I always forget to do this. I think that's better. Okay. You know, the mean is around 64 inches tall, and as we go further, you know, we have some women who are 6 feet tall, but not very many, and we have women who are, you know, 4 foot, I don't know, 10 or something, but not as many as we have people who are around 5'5", okay? So this is what our population looks like, okay? And we can ask, in this case, we've got 100,000 people, and so we can ask, what is the actual mean of our population? And we see the mean of our population is, you know, 64.49346. So that is the actual mean of all 100,000 people. And we can ask, what is the standard deviation of our population? And this is the actual standard deviation of all 100,000 measurements here. Is that okay? And I can just say, you know, give me the first few values, and we see, okay, so here's people who are 2 people who are 68 inches. We have somebody who's 62, and so we have that, okay. And what I'm going to do is use this function called sample. And sample says, well, from the population, do random sampling, and what I want is I want 10 people, okay. So if I say, go into the population and draw 10 people, this is, it randomly selected 10 people, and these are the heights of the 10 randomly selected people from the population. Is that okay? Okay. And if I, every time I run sample, it goes in and it pulls 10 different people. Okay. So in order to deal with that, I'm going to just create a variable called, I'm just going to call it SMP for sample. And that way I can say, so we don't see it until I ask for SMP, and then I can say, well, calculate the mean of that sample of 10 people. And so the mean of these 10 randomly selected people is 66.9. I can ask for it to pull another sample, just rerun the command, and if I ask it to calculate the mean, and so the mean of these 10 randomly selected people is 63.7. Okay, so it's convenient to just take samples of 10, because when you have whole numbers and you add them up and you divide by 10, you're only going to have one decimal place, right? Okay, so I want to do this repeatedly. I want to do this maybe 1,000 times or something like that. Okay. And so what I'm going to do is I'm going to build a loop. Okay, and so I'm going to create a loop, and I'm going to say for I in 1 through 1,000. Okay, so it says do this basically, and what the loop does is it's going to just run the commands within these curly braces, and it's just going to run through it, and once it reaches the end, it goes back to the top and it runs it again. And every time it goes through it, it just increments I from 1, and it increments it to 2 all the way until it reaches 1,000, and then it stops. Okay? So basically I'm just going to say draw a sample from the population of 10, and then I want you to take the mean of the sample. Okay? But what I want it to do is I want it to record the mean of that sample somewhere. Okay? So I'm going to just record it in a variable called sample means. Okay? But what I want it to do is I want it to store all 1,000 of those sample means. So I'm going to create basically a subscript that says the first time you run it, I want you to store it in location 1 in sample means. So essentially what I'm doing is I'm creating kind of like a drawer called sample means, and there's going to be 1,000 locations or 1,000 spots where I can store values. And the first time it runs it and it calculates the mean of the sample, it's going to store it in the first location. It runs through the loop again, and it stores it in the second location. It runs through the loop again, and it stores it in the third location. Okay, and every time it does that, it increments from 1, 2, 3. So this is automatically going to do. And so all I have to do is I just have to tell R, listen up, this thing is coming. So I'm just going to start off with sample means being an empty thing, and then it's going to run through the loop 1,000 times. And each time it's going to store the mean of the sample of 10 and store it into sample means in location I, where I goes from 1 to 1,000. Does this loop make sense to you guys? Okay, so I'm just going to have R run through that. Very quick and easy. We're done now. Okay, so sample means now has 1,000 values in it. Okay, and we can even look at all 1,000 values, and this is all 1,000 values of all those sample means that it created. What is the histogram of our sample means going to look like? So this is the histogram of our population. What is the histogram of our sample means going to look like? Similar. Okay, similar but different, right? How is it going to be similar? How is it going to be different? So let's think about this before we create the histogram, okay? So if you think about the heights of women you might encounter in the United States, it makes sense. Most women you encounter are, between 5 feet and 5'10" or something like that. Some people are taller than that, some people are shorter than that, but that's going to be the bulk of your majority here, okay? Now just imagine random groups of, now I don't know how often we do this, but random groups of 10 women, and we take the means of those 10 women. And then let's say we just created another histogram of all the different random groups of 10 people, 10 women. What do you think the mean of that sampling distribution will look like, or will be? So the mean should be around the same of 64.5, but what about the spread? The spread is going to be smaller, right? So as for individual women, if we see an individual woman who is 6 feet tall, we'll say, oh, she's on the taller side, or she's rather tall, but it's not going to be extremely unusual or mind-blowing if that happens, okay? However, if I said I picked 10 random women, not 10 women on the volleyball team or 10 women who play basketball or professional basketball players, I'm saying I'm picking 10 random women, and the average height of those 10 randomly selected women was 6 feet, that would be rather surprising, right? because if they're truly random, you would not expect all 10 women to have an average of 6 feet. Okay, if I said I picked 10 women from the WNBA and the average was 6 feet, you'd be, oh, well, that makes sense. Okay, but if 10 random women had an average of 6 feet, that would be rather surprising. So we would expect a smaller spread. So we can create a histogram, and because there's only 1,000 people, we might not have this as nice of a defined normal shape. Okay, so I can do a histogram of sample.means, and I'm going to do breaks equals, we'll do like 20. Okay, yeah, maybe I'll bump it back up to 30. So we get, this is the shape we get, okay? So it's not as nice of a shape, and we can fix that by just continually taking more, okay? So this slightly odd shape we see. We get, okay, and we do see that the average is indeed around 64.5, and the spread is significantly smaller, in that we don't see the mean ever being over 68 inches, okay? So the highest that we observed was 68. So let's just compare this histogram with the other histogram. Oops. This one being, 68 is around here, and the lower end being 60 over here. In this histogram, we're going from around 61.5 to 68. Okay. So actually, if I took 1,000,000 samples, okay, so our original population only had 100,000 people in it, but I'm going to take 1,000,000 samples of size 10. Okay, so I'm taking 10 people, I'm throwing them back in, and I'm going to do this 1,000,000 times just so we get a nice distribution. It's going to take a little while to generate just because we're asking it to do something 1,000,000 times. But it's a computer, so it doesn't mind. Okay, we just have to wait a little bit. Okay. And actually, it's in R, the best practice is to avoid loops when possible. You can do things in vector notation. I probably should have just done 100,000 or something like that, but we're asking it to do 1,000,000 times. Oh, I might regret this. I'm gonna just tell it to stop. I wonder how far I got. Sample means, got to, when I told it to stop, it had finished 132,000 times. Okay, that's good enough. We don't need to do it 1,000,000 times. I've learned my lesson R. Okay. So I'm going to ask it to create a histogram of the 132,000 or 133,000 almost samples that it looked at. Okay, and we have a nice. This looks nice and normal, right? Very, very normal shape, and I could do a QQ norm. Is it? We can do a normal probability plot. Okay, and so that looks about as straight of a line as you can get. Okay. Okay, going back to the histogram, we have that, and then I can ask for the mean of the sample means of all something that we got, and the standard deviation of the sample means. Okay, so again, the mean of the population was 64.49346. The mean of, the 130,000 sample means, okay, so this is a mean of sample means. Every time we take a sample, we calculated a mean of 10 people, and then we're taking a mean of all of those different sample means that we took, okay? And then I can ask for the standard deviation of the population. So the original population had a standard deviation of about 3, but then when I take the standard deviation of all the different sample means, the standard deviation is now much smaller at around 1, okay, 0.95. So indeed, that reflects our intuition that the standard deviation of the sample means is much smaller than the original population. Okay, is that all right? Yes?
Didn't you survey the same amount of people? Because population was 100,000, right?
Mm-hmm.
And you ran it about 132,000?
Uh-huh.
So why is it smaller?
So the population is we're looking at individual women, one at a time. Are there women who are 6 feet tall? Yes, okay? When I take a sample, the sample means, on the other hand, is I've taken random samples of 10 women at a time. And I'm taking the mean height of those 10 women. So the random sample, we're boiling down to a single number. We don't care about the individual women that we selected in that sample. We're just boiling that sample down to a single number. And then with that single number, we do this over and over again. So I generate 130,000 sample means, and we're looking at the distribution of that. Okay. Okay, so the distribution of sample means has a smaller spread than the individual women themselves. Okay. What if I took, instead of samples of 10 women, I took samples of 100 women instead? What would happen then?
Closer to 3, right?
Yeah, the spread will get even smaller, right? The mean of those sample means is still going to be close to 64.5, but the spread between sample means of samples of 100, the spread will be even smaller. Okay, and so I will just demonstrate that, and I don't want to bore you guys to tears here, so maybe I'll just do this 10,000 times, and I'll take samples of 100. And let's try this. Oh, okay, and let's look at the histogram of sample means now. Okay, so this still looks normal, but if we look at the range on the bottom, we see it's very small. It goes from 63.5 to 65.5. I can ask for the mean of sample means and the standard deviation of sample means. And we see the mean is still around 64.5, 64.4938. And the standard deviation is now only 0.3. Okay, so so the standard deviation is even smaller now. Okay, and that matches our intuitive sense. Okay. Is that all right? Okay. What would happen? So in this case, our population had a normal distribution. What if our population was not normally distributed? What if our population had a uniform distribution? Let's say we just asked, what's the last 2 digits of your phone number? Okay, and we would expect around the same number of people to have the last 2 digits of 17 as the last 2 digits of 83 as the last 2 digits of 45. Okay, if we looked at a whole bunch of different people. So in this case, I'm going to generate a new population, and this will be our unif, and we'll say our unit times 100 from 0, and I think actually I want floor. Let me just make sure that okay. So if I do a histogram of population, and it's just, we get a uniform distribution. This is just an artifact of the way the histogram is drawn, in that the bin over here includes 0, and this one, whatever. It's fine. This is just a funny artifact of the way the histogram is drawn. Okay, but it is uniformly distributed. Okay, so what would happen if I create a sampling distribution here? Let's say I drew samples of 30 people. And we say, give me the last 2 digits of your phone number. And we're going to, for whatever reason, we want to take the average of the last 2 digits of your phone number. Okay? I know that doesn't quite make sense, but let's just say we just did that. All right? We've got a uniform distribution. Okay, so we would expect, so the mean of this, of our population here, right, is like 49.5, right? Because we can go anywhere from 00 to 99. Okay, and so the mean is 49.5, and the standard deviation of our population looks like this, okay? All right, well, let's go ahead and just see what happens, all right? We're going to do this 10,000 times. All right, histogram of our sample means. Let's see. The histogram takes on a normal distribution, okay? And I can ask, what is the mean of these sample means? The mean is still around 49.5, and the standard deviation is not 28.8, but it's 5.3. Okay, we've taken samples of size 30. Okay, and when we take samples of size 30, we end up getting a normal distribution. What's going on here? Well, this we're not getting a uniform distribution, okay? Because to get a uniform distribution means I would have to, we'd pick a range from 0 to 99 or whatever it might be, and it doesn't make sense that when I pick 30 random people, that it's just as likely to get an average of 10 as it is to get an average of around 50 if we're just taking 30 random people. Okay, so we're not getting a uniform distribution. We get a normal distribution where numbers close to the middle are much more likely than the numbers far away from the middle. Okay, and that concept is known as the central limit theorem. Okay, so I think this is good enough for little demos with R. R is neat, right? Is this useful in illustrating sampling distributions? Okay, good. Yeah, we don't even need to bother. Our studio never loaded over here. Here's our little mouse friend. Okay, we'll save here. Okay. So we have something called the central limit theorem. Okay. And the idea behind the central limit theorem is that we have a population with mean mu and standard deviation equal to sigma. Okay, and we generate a sampling distribution from this population. Meaning we repeatedly take samples of a defined size, of size n. Okay, so all the samples we take to generate our sampling distribution have to be of the same size. You can't take samples of 100 and samples of 10. If you pick samples of 100, you take samples of 100 every single time. So we repeatedly take samples of size n and calculate y bar for each sample. Okay. Then the sampling distribution of y bar will follow the normal distribution under certain conditions. Okay, the sampling distribution of y bar will have a mean of mu, and we'll have a standard deviation of sigma over the square root of n. Okay, and this is essentially what the central limit theorem says. And so let me just expand what we mean by under certain conditions. So the conditions so that the sampling distribution is normal. Okay. Well, the conditions, I guess, one condition is that the samples themselves must be randomly selected. Must be randomly selected, and individuals must be selected independently of other individuals. So you can't take groups of people together. So independently. And then we have the sample size is not too big, and the rule of thumb is less than 10% of the population if selecting without replacement. So selecting without replacement means when you select someone, you're like when you draw a card out of the deck, you're not putting it back in, okay? And the reason being, you can think of it this way. You know, let's say you have a deck of cards. In the beginning, there's 52 cards. Half are red, half are black, right? 26 red, 26 black. After you draw out the first card, let's say it's red, then there's 25 red cards and 26 black cards. In the beginning, it doesn't really. When you only taken out one card, the change that it makes to the rest of the population is rather minimal. Okay, and so if it's less than 10% of the population, it's not that big of a deal. But once you start taking more than 10% out of the population, what you have in the sample could affect what's left in the population, and so that actually violates this idea that individuals are selected independently, being that what's in your sample now has an influence on what might be selected in the future. Okay. Of course, if you're selecting with replacement, as in you take a card out and you put it back in and then you shuffle it and then you draw another card, then you can take as big of a sample as you want. That doesn't matter. Okay. So sample size is not too big. This is rarely a concern in life science applications because usually the population is everybody ever, and so you don't have to worry about taking more than 10% of the world or of America or whatever it is that you're looking at. But the other problem, sample size is not too small. This you might run into, okay? And this so sample size is not too small. I need to expand on this a little bit more, so let me just slide this up here. Okay, so if the population is normal, any sample size is fine. Any sample size is okay. So if the population has a normal distribution, you can take sample sizes of 2, and that will not be too small. But if the population is not normal, then you need a bigger sample. Okay? If the population is not normal, larger samples required. And this is just a very vague rule. We say n equal to 30 is big enough for most cases. But if you have something extremely skewed, n equal to 30 might not cut it either. Okay, so something like income distribution is very skewed. You've got people making millions versus people making only thousands per year. You know, a sample size of 30 is not going to result in a normal distribution. Okay, you'd probably need to turn income into on a log scale to deal with it. And, you know, you take the log everybody, but then you're dealing with log dollars, which nobody understands. Or you have to take an incredibly large sample. So if you have a really skewed distribution, sometimes there's just not a whole lot you can do to make it normal. But for most cases, n equal to 30 is fine. Okay. All right, and so that is the central limit theorem, and it applies to any distribution. Okay, so even if the distribution is uniform, okay, the sampling distribution of y bar follows the normal distribution, and we saw that in our little R demo. Okay, when we looked at the last 2 digits of a phone number, which had a uniform distribution, the sampling distribution still followed the normal distribution. Okay, and the book has this nice little illustration, and it says, you know, just imagine another distribution. Whoops, I guess that's fine. Where the distribution looks like this. Okay, and what it is we measured how long it takes a person to hit a push button with their forefinger. Okay, so I don't know, a light flashes and you got to go and you hit the button. Okay, and most of the time people do it relatively quickly. Okay, but then every now and then the person fumbled, they messed up, they missed the button, or they messed something up, and so the amount of time they took is longer than it should have than that. So you have like a bimodal distribution where you've got this weird, you know, a smaller peak, but, you know, non-negligible one over here. Okay, so this is what the actual population looks like. What would happen if we took random samples from this population? Well, in the beginning, you take small samples, you can still see that funny little peak. Okay, as the number of samples get bigger and bigger and bigger, that funny little peak starts to go away, and around n equals 30, we can see that we don't really see the effect of the peak as often. Okay, and by samples of size 60 and 128, the resulting shape looks very, very much normal. Okay, so this central limit theorem of everything turns normal is rather remarkable, but it holds true. Okay. So, that was one where, you had a fairly skewed distribution, but you end up getting something normal as, when your sample size got really large. So let's just try a simple application, okay? The thing to keep in mind is that the sampling distribution of y bar will follow the normal distribution, have a mean of mu, and standard deviation of sigma over the square root of n, given that the population has all of this stuff. So I'm going to just copy all of this. We'll make a new slide. Oops. Let me shrink this down. Slide this up. Okay. So you guys remember your stuff from the normal distribution, and let's try a little problem here. So I'm going to say, all right. So we'll say IQ scores come from a normal distribution, mean 100, standard deviation of 15. I said this is shorthand, right? All right. So let's say I'm going to have two questions. Part 1, if we randomly selected one person, what is the probability he or she has an IQ over 115? Okay. And then question 2, we randomly select uh, 16 random people. What is the probability that the average IQ, all right, let's change that from 16 to, let's just do 8, okay, because I think 16 will be too much. What is the probability that the average IQ of the 8 random people is over 115? Okay? So try that out. Try both of those questions. What we got there? Okay. Did we get these answers? Yes, no? Oh, I'm on mute. I know I have low battery. Give me a second. Okay. How are we doing? Okay? Yes, no? Alright, so this one is, the first one is just a regular old normal distribution problem, right? We got this, we're centered at 100, and I'm going over to 115, and I want to know how much is over here. So my z is equal to 115 minus 100 over 15, and I get a z-score of +1. And I look up 1.0, and I can find the area to the left. Area to the left of 1 is equal to, what is it, 0.8413? Is that right? Okay, and so the area to the right is equal to 1 minus 0.8413. And I get 0.1587. Or conversely, I could have looked up the area to the left of -1, which would have been the same thing. And so the answer to number 1 is 0.1587. It's a regular old normal distribution problem, which we covered last week. Or last week. Yes. You guys have your reference tables, right? Okay. If I wanted to do this in R, what would I do? 1 minus P norm, 115, 115. We're going to type that into R. Okay, so is that okay? Feedback? We're good. All right, over here, very similar, except we have to create the sampling distribution for y bar. So the sampling distribution of y bar has mean what? Has mu equal to mu of the original. So mu is still 115, but the standard deviation is sigma over the square root of n. So it's going to be 15 over the square root of 8. So whatever 15 over the square root of 8 is, 5.303. So now, similar question. I've got, 100, and I want to go over to 115 and find the area over here. So my z-score, 115 minus 100 divided by 5.303, and I get 2.83, I believe. Okay, and I look up the area to the left of 2.83, and I get 0.9977, which means the area over here is 1 minus that, 0.0023. So we have almost a 16% probability that an individual has an IQ over 115. But if we're taking 8 people at random, and we ask what's the probability that 8 randomly selected people have an average IQ of 115 or higher, that's now only about 2 in 1,000. So normal distribution, this is application of the central limit theorem. Okay, so we use the CLT over here to define our sampling distribution. Do we want another practice problem, or are we feeling good?
Is this where, is this just kind of normal distribution, how IQ scores got set up this way? Because 115 is exactly,
I don't know the full history of how IQ scores were developed, but they do have these targets in mind, so that. And there's 2 IQ tests, and one has a standard deviation of 16 and the other one has a standard deviation of 15, but they're kind of both targeted. They develop and they pick the questions in this way for that. Okay. All right, well, let's see. Why don't we take a short break here, and then we'll come back and we'll delve into chapter